Characteristics of exponential. So this unit is going to be exponential and logarithms. So it's chapter 7 and 8 out of your textbook. An exponential function, it can have growth or decay. So with growth, they use examples like bacteria, how it can grow exponentially. For example, you can have like one bacteria in bacterial cell in a petri dish, and if it like doubles every, I don't know, 10 minutes, it's going to grow really, really quickly. So it'll double. So from 1 to 2, then 2 to 4, then 4 to 8, then 8 to 16, then 16 to 32, then 32 to 64, 64 to 128, and eventually it just grows really fast. So with exponential graphs, you're going to see an exponential growth. So it'll look like this, where it just slowly goes up, and then all of a sudden the graph shoots upward like this for growth. Or you're going to look at a decay, where it may start up here somewhere high, and then it comes down and it decays almost out. So an example of that would be like radioactive material. So when you go to a doctor and they want to do a scan of you, sometimes they put radioactive material in a person. They make it have a really large half-life, like it halves very quickly, so it doesn't last in you very long, because really you don't want to be like walking around for months with radioactive material inside of you. So it decays really quickly. So consider there are infinitely many possibilities for B, and therefore infinitely many possible exponential graphs. So we're going to look at the exponential equation. It's in the form y equals a b to the x. We're going to look at transformations of it tomorrow. So they don't give you that version of it. So if you look up their laws of logarithms, underneath laws of logarithms and the growth and decay, this is the formulas you're using for these two chapters. So we're going to look at y equals 2x. So if you're looking at y equals 2x, then a would be 1 and b would be 2. So we're going to look at this. It would be technically 1, 2 to the x, technically. But we can just put it in as y equals 2 to the x. The only thing that is to the x is the 2, not the 1. So we're going to graph this function using our calculator. So punch in y equals 2 to the power of x, to the exponent x in your calculator. So we're going to go... So in your y equals, you're going to put 2 to the exponent, so to the power of x. Press graph. Oh, mine's set. I'm going to go zoom 6. So what you're going to do is you're going to go to your table of values. So second table, and you're going to fill in the y values for it. So at -3, we have 0.125. How did they get that answer? You're literally just filling in the x value into the equation, right? So y equals 2 to the x. So y would equal 2 to the -3. 2 to the power of -3 is 0.125. So your calculator just does that all for you instead of you having to do every single one separate. So we're going to go second graph. -2 is 0.25, which would be y equals 2 to the -2, etc. -1 is 0.5, 0 is 1, 1 is 2, 2 is 4, 3 is 9, 4 is 16. 3 is, yeah, that is an, oh, it's 2 to the 3, which is 8, sorry. No. That's an 8, because this would be 2 to the power of 3, not 3 to the power of 2. Okay, and we plot it on our graph. So, if I plot these, I'm going to get -3 and 0.125, so very close to the x-axis, but not exactly on it. And then -2 and 1/4. And then -1 and 0.5. 0 and 1, 2 and 4, 3 and 8, and the rest don't fit. Now, what it's doing, if I keep filling in like -4, -5, -6, -7, you're just going to get super, super, super tiny decimals, but they're still positive, right? So these are just going to get closer and closer to the x-axis, but they're not going to touch the x-axis. So it basically runs along the x-axis. Imagine that's a straight line because it's not drawing it straight. This here would be a straight line running along the x-axis. The reason why it runs along the x-axis is that's an asymptote on your x-axis. So you actually have a dashed line along your x-axis. So this dashed line causes the equation to curve. What? Don't worry about that. It's just the same thing. You're just going to the -1, to the 0, to the 1, to the 2, to the 3, to the... So would this be a growth or decay? It's growing, right? It's going from smaller y values all of a sudden to really big y values, right? As you go along, as your x increases, your y increases. So it's growing. Okay? What's the domain of this graph? Infinity. That's what everyone said. Infinity. So we could say in set notation, XER. Or we could say in interval notation, -infinity to positive infinity. Because every x value exists. Because this is going to keep going out wider, 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 wider forever, right? What's my range? Yeah, so it's going to be y is greater than 0, or from 0 to infinity, because you can't equal 0, that's where your asymptote is. There's absolutely no graph down here, right? So it's going to be y such that y is greater than or equal to 0, YER, or not greater than or equal to, y is greater than 0, because it's not equal to it. And then you're going to have round bracket 0 to positive infinity round bracket. Both of these are round because you can't equal positive infinity and you can't equal 0 because that's where the asymptote is. What's the asymptote? A lot of people will tell me x equals 0. On the x-axis, x equals 0 is every single value on the y-intercept, right? That's how you find a y-intercept, x equals 0. So this isn't x equals 0. This is what? Y equals 0. Whenever you have a horizontal line, it's a y equals line. Whenever you have a vertical line, it's an x equals line. So your asymptote is at y equals 0. Now, what happens if we put a vertical translation on the back of this? So y equals 2 to the x plus 1. It's going to move that asymptote up 1. Or if I put a minus 1, it's going to move it down 1. The only thing that affects your horizontal asymptote, because this is a horizontal asymptote, is a vertical translation, which we're going to learn tomorrow. But the only thing that affects this horizontal asymptote is a vertical translation moving it up or down, because you can't stretch a line, making it thicker. Vertical stretch isn't going to affect it. And horizontal moves everything this way, so that's not going to affect it. So the only thing that affects this is a vertical translation. So basically, whatever your vertical translation is what your asymptote is. Okay? Your intercepts, unless there's a vertical translation on here, you're going to have no x-intercepts, because the whole thing's above. The whole entire x-axis here. So you have no x-intercepts. What's your y? That's 0 and 1. So if b is greater than 1, so this b value was 2, right? Our a was 1. Our b value is 2. If b is greater than 1, you get the shape above. This is called an increasing exponential function, or a growth function. So we're going to look at y equals 3 to the x. The value of a in this case, you'd have to go y equals 1. times 3 to the x. So the value of a for this one is 1. What's the value of b? 3. If you put it into your calculator, good. Don't want that one. If you put 3 to the power of x, it still passes through 0, 1. Still has y-intercept at 0, 1. But I want to go like this. I want to go 2 to the power of x, and then 3 to the power of x. I'm going to make b thicker. So you can see what happens in the increase. So the first one is 2 to the power of x. Next one's 3 to the power of x. It drew it so thick that it actually makes it look like it's on the x-axis, which is not. So if I put in, what was the next one? 4 to the power of x. What's happening? Still passing through 0, 1. It's just growing faster. Does that make sense? The larger my b value is, it should grow faster. If I do 2 to the 2, if my x value is 2 on the graph, 2 to the power of 2 is 4. If my b value is 3, 3 to the power of 2 is 9. So at 2, it's going to be at 9 for the 3 to the x graph. 2 to the power of 4, it's going to be at 16. Oh, try again. 4 to the power of 2, it's going to be at 16. And then 5.25 to the power of 2, it's going to be at 27.5625. So it's growing faster, right? So those are all the same x value of 2, but it was with the 2 to the x graph, it was at 2 and 4. With the 3 to the x graph, it's going to be at 2 and 9. With the 4 to the x graph, it's going to be at 2 and 16. With the 5.25 to the x graph, it's going to be at 2 and this. So it's going to grow faster, so it's going to look like that, right? It grew faster. So all of these ones in particular had values of 1 because they don't have an a value in front of them. This one has a b value of 4, and this one's 5.25. And they also had y-intercept at 0 and 1. How do the different bases affect the function? This is called a base. The b is the base, which is kind of nice. So the b value is your base. What does the base do? The larger your base, what happens? The faster it grows. I should say faster the graph grows, but same thing. Ooh. There we go. So what happens if our a value changes? So we have all the same b values for these ones, but our a value changed. Let's look and see what happens. So here we have 2 to the power of x, just the basic one. Okay? Our value of a is 1, right? Because this would be y equals 1, 2 to the x. Our value of b is 2, and our y-intercept was still 0 and 1, right? That was our original. Now what happens if we have a 3 in here? Let's watch this. So we're going to go bracket 3, bracket 2 to the x. You could just put the 3 without brackets, but the 2 to the x you have to put in brackets. The reason why you have to put the 2 to the x in brackets and not for sure the 3, unless you have a calculator where your exponent pops up, then you don't have to worry about this at all. you'll have to go 3 times 2 to the x in your calculator. You can get away without brackets if your exponent goes up. Because you want the x to only be to the 2, okay? So this is the original 2 to the x. What am I going through now? My y-intercept. So I look at these ones over here. When x equals 0 for the first one, y equals 1. When x equals 0 for the second one, y equals 3. Value of b is 2. The value of a is 3. Why would that happen? Remember yesterday I said to you, well, actually, whenever you hear y-intercept, you should think x equals 0, correct? So if I plug a 0 into x here, 2 to the 0 is just what? 1. Anything to the power of 0 is just 1. So your y-intercept is going to be this 3 then for these cases. So in this case, if I fill a 0 in, give me 2 to the 0 times 4. So my y-intercept is going to be at 4. And this one's going to be at 5.25. How do different coefficients affect the function? This value in front, what is that? If we did transformations. It's a vertical stretch. So it's stretching that graph upwards. Okay? How do different coefficients affect the function? My only biggest catch on this is that people will always say that this a value is the y-intercept always. That's not the case. If I put like a vertical translation at the back, like a +1, it's going to change your y-intercept, right? Like if I had y equals 3, 2 to the x, everyone will say, oh, my a value is my y-intercept. So it's going to be, because I plug a 0 in here, this cancels into 3. True? But what if I put a vertical translation 1 up at the back? What actually is my y-intercept of this one? 4. It's not 3 anymore. So you can't just say that my a value is always my y-intercept. Don't do that. Don't be that person. Okay? Easiest way to find your y-intercept, truthfully, plug 0 in for x and just solve it. Okay? Don't try and make a rule that's going to work forever. So that's if b was greater than 1. Now we're going to look at ones where b is between 0 and 1. We never look at b negative. You can't do b negative. Okay? So here we're looking at 0 is less than b is less than 1. The other ones we looked at were b is greater than 1. So let's plug in 1/3. It's decaying, right? So let's plot our points. We have -3 and 27. Well, why would that be? Because we'd have 1/3 to the -3. When you have a negative exponent, you'd flip it. So that technically would be 3 to the +3, which is 27. -2 is 9. -1 is 3. 0 is 1. 1 is 0.33. And then 0.11. 0.3704. So we're just getting really small is all. Right? And when we plot those, we can plot -2, 9, 9, -1 and 3, 0 and 1, 0.33. We're just getting way closer, right? Now all that's going to happen is I'm going to get closer and closer to 0, but I'm not going to touch 0. So once again, I still have an asymptote at y equals 0. Now with 30-2, we never have any vertical translations on it. So we can always say A is the y-intercept. We also never have negative 8s. So for now, you guys have dealt with negatives or positive A's, right? That's what we've like right now, positive 1, and we did positive 4, and we did positive 5.25 and positive 3. If we have a negative A value makes you have a reflection in the x-axis. So it's actually going to make this graph increase. So you can't just say always that when b is between 0 and 1, it's a decaying function. You can only say that if a is greater than 0, if a is positive, right? So the domain is XER, again, or negative infinity, positive infinity. The range, once again, is y is greater than 0, or 0 to infinity. The asymptote for this is still y equals 0, and my intercepts are no x-intercept. My y-intercept is at 0 and 1. So if 0 is less than b is less than 1, you get the shape above. This is called a decreasing exponential function. Or a decay function. Remember, though, if you get a negative a, it actually does the opposite. So if 0 is less than or equal to b is less than or equal to 1, and you have a negative a, you actually have an increasing function. And if b is greater than 1 and you have a negative a, you actually have a decaying function because it causes that reflection in the x-axis, which we're going to deal with tomorrow. This I want you to look at. So some people say, well, why? Like, what the heck happens here? Y equals 3 to the x and y equals 1/3 x. We can only compare these. We can only compare these two graphs if we actually have the same base. Right now, one base is 3 and one base is 1/3. I can't compare them. So whenever you do transformations, like you're going to do tomorrow, the only way you can compare exponential equations is if they have the same base. Like one's base 3 and the other one's base 3. Please star this, keep it in your toolbox because this is one you want to keep. How could I make 1/3 be base 3? Because the only way I can compare these is if I made it be base 3. How can I make 1/3 be a 3? How can you move? Yeah. Yes. If I make this be a negative, so -1. If I take this 3 on the bottom and I want to get it up here, correct? I want to get the 3 up and I want to move the 1 down. Remember yesterday when I gave you this, for example, 3, and I gave it to the -1, and I told you needed to write it as a positive exponent? You could write it as, this is technically like this. This would move down, this would move up, so it'd be a 1/3 to the positive 1, right? Same thing here. I can make 1/3, make that 3 move up and the 1 move down, and make this be equal to 3 to the -1x. We agree? So now I can compare them. I'm just going to write it down here. Y equals 3 to the x, and y equals 3 to the -x, technically. What does a negative in front of an x do? Transformation rules, just as you've been taught every single time. Yeah. It reflects in the y-axis. You get a reflection in the y-axis. Let's prove it. 1/3 x and 3 to the power of x. Reflection in the y. Okay? Go away. Okay. Given the points -2, 16, -1, 4, 0, and 1, what's the function of the form y equals c to the x can be used to describe this graph? So we have 2 to the 16, -1 to the 4, 0 to the 1. Remember, we're doing something to our x to get our y, right? Something to our x to get our y. That same something to our x to get our y. Okay? It's a base to the x. A base to the x. So we need a base, some sort of base, to the exponent. X should equal our y. We agree? So for this point, we have something to the -2 should equal 16. And for this one, we should have something to the -1 should equal 4. And for this one, we should have something to the 0 should equal 1. This one's not a real giveaway. Anything to the 0 is 1. It's more these two that it's going to have. What base could I put in here that would get me 16 and 4? Let's try 2. If I put a 2, 2 to the -2 is actually a 4th. So that's a problem. Okay. What about 3, 4, 5? What do you think it should be? Yeah, a quarter. Some people will tell me it's 4. 4 to the -1/2 is 1 over 16. So 4 gets me the answer, but not the right way. If I did 1 over 4, then it would work. 1 over 4 to the -2, sorry, is the same as 4 to the 2, which is 16. 1 over 4 to the -1 is the same as 4 to the 1, which is 4. And then this one just works because anything to the 0 is 1. So you're right. So what function could we do? Y equals 1/4 x. And this is your homework.